Go. Hello and welcome back to Statistics1 after this exhausting break for no reason. We are going to continue chapter 4 on probability. Last time we talked about that probability is a chance that something will occur. And today, that's something we're going to define as an event. So, the chance of you rolling number 3 on a die is 1 out of 6, if it's a fair die. The chance of you picking a particular card out of deck is 1 out of 52. Or, the chance of picking a black card would be 1/2. So, probability was simply the number of number of outcomes that you desire divided by the number of all possible outcomes. So you desire to pull the black card out of the deck that has 52 cards, and half of those happen to be red and half happen to be black. So, right, you have half chance. The same thing would be to flip a coin. There's no difference actually in probability from flipping a coin or picking a card if you're looking for a particular color. Because the coin has 2 options, right? Heads and tails. So it's 50-50 chance to get either or. And then the cards have half a deck is red, half a deck is black. So it's 50-50 chance to get the black card. It's very simple, right? So today we're going to define sample space event. And I'm just going to take a look into some of the relationships that we get. Using Venn diagrams, that's your favorite stuff, right? So, definitions first. The definition of an sample space. So, sample space is the collection of all possible outcomes of an experiment. Collection of all possible outcomes of an experiment. As I said, deck of cards has 52 cards. That would be your sample space. You have to pick something out of those 52 cards. You can't go looking for a red, Queen of Hearts, and pick out an elephant, because the elephant is not in the universe of 52 cards. So your universe from which you're picking things for the experiment is called a sample space, and that's all possible outcomes. You have a dice, right? A die with a 6-sided die. On it you have 6 different numbers, 1 through 6. Now, are there different ones? Yes. There's that game, Dungeons and Dragons, right? They have whatever amount of different sides and possibilities on whatever they roll there. So you can change the rules of the game, but then immediately your sample space would change. So sample space for a game called Flip a Coin would be heads and tails. Very simple. So sample space for the coin is heads or tails. Very simple. For the cards, it's going to be 52 cards. Each individual card has its characteristics. It's a face or non-face, it's black or red, it's hearts or spades, or right? So you have all of those. And now we have definition for the event. A collection of outcomes for the experiment that is any subset of the sample space. An event occurs if and only if the outcome of the experiment is a member of an event. We'll talk about this. So, a collection of all possible outcomes for the experiment in parentheses, subset of the sample space. An event occurs if and only if the outcome of the experiment is a member of the event. So an event occurs if and only if the outcome of the experiment is a member of the event. So, picking a black card is an event. Picking number 7 is an event. Picking a spade is an event. And these events can be having something in common or not. You can pick black or red card. See, you can't pick a single card and then win, because none of the cards is black and red at the same time. So the event is the part of the sample space. It is what you are trying to get. And then the events together could be overlapping or not. So let's think about. So event is what we want to get. Let's say, if you want me to rephrase the red statement. So here's an example. Pick a red card. So that's an event. Another. Pick a spade. Pick a 7. All right, great. So when you are thinking about all of these, these are 3 separate events. So these are 3 separate events. And we know to find the probability of each one of them individually. To pick a red card, it's a 1/2 probability. To pick a spade is 1/4, right? Because you have 4 suits. Spade is one of the 4, so 1/4. Pick a 7, well, you have 4 of those, so 1/13. We did this last time in 4.1. Probability for each individual. Today, we want to just make sure that some of these events can work together and some cannot. Pick a red card and pick a spade. Can you pick a card that is a red spade? No, right? You can't, because all spades are black, right? In the deck. Great. So A and B cannot be. How about that? You cannot pick a card that it's red and a spade, because all spades are black. We cannot pick a red spade because all spades are black. None of them are red. The same thing like you can't pick a black heart, right? That's another thing. Now, can you pick a red 7? Yes. We can pick red 7. There are 2 of those, right? Diamonds and hearts. So there are 2 red 7. So we can pick red 7. So A and C can work together. And can you pick 7 of spades? Yeah, there is 7 of spades in the deck, right? You have 4 7s. 7 of hearts, 7 of spades, right? So there is, so we can pick seven of spades. So B and C can work together. So this is just something to think about. So there are certain things that you can do and certain things that you cannot do. So you cannot pick a red card that is black. That makes no sense. You cannot pick 7 that is a 2. That makes no sense. You cannot pick a face card that it's a 7 because none of those are 7s, right? So there are certain events. If you say face card, picking a face card is event, and picking a 7 is event, well, they don't work together because one and the other do not intersect anywhere. So now, thinking about this, we are able to have visual representation of these events using Venn diagrams because they are easy to show all of this. So we have a situation over here, which is, so this box is going to be your sample space. In Venn diagrams, it's called the universe, but we call it sample space. So sample space, and you have an event. So this would be your event A. And then, and I'm going to shade what I'm talking about. Then you can have a complement of the event, meaning everything else other than event you are looking for, and we say not A. Let's say you have a game where you pick a card, and if you pick 7, you're getting executed. Any other card, you are going to win $1. Are you playing it? Whew, huh? Look, my choices are over here. What are the odds? So, $10. Now, all right, $10. So you pick a 7, you're getting executed. Anything else, right? It's very popular in North Korea. Anyway. Let's take a look at another possibility, and this is when events overlap. So now I have 2 events, event A and event B, like we had earlier. Now, this is AND. A and B. The intersection between 2 events. Intersection between 2 events. and here is or. A or B. So and is restrictive and or is loose. For and, well, you know that. License and registration, right? There's no wiggle room, right? There's no wiggle room when there is license and registration. Now imagine officer walking towards the car, leaning onto the car, saying, give me the license or registration or your library card, whatever you have. You see how loose that is? Like anything. So technically, they're very different from each other. The event A and B, it's very restrictive, very to the point. I want this, and nothing else makes me happy. Which is why it's shaded in the middle where A and B have common ground. So if I want a red card and the face card, it's a very particular, right? So what is a red and the face? So event A, red card, B, face card. So what would be the event? Event A and B. Well, it would be all red cards which are face cards at the same time. So what do I have? Same time. So what do I have? I have Jack of Hearts, Queen of Hearts, King of Hearts, Jack, Diamond, Queen, Diamond, and King. I should have put these symbols in front, right? Yeah, whatever. So this is AND. And you exactly have 6 out of 52 cards. So 6 out of 52 is the probability to pick a card which is both of these events at the same time. 6 out of 52, which is 3 out of 26. So that's your probability to pick. Now, event. So event A or B. Oh, now these are all of the cards that are either red or face. And that's a lot of cards. Do I have in this, there it is, full deck. Now let's see if I can make this. No, I don't want to search it. Can I do? All right. Or maybe I can do, let me see. So now I'm going to switch to all right. Oh, maybe if I switch. So what I have here displayed are all of the cards that are in the deck. 52 cards, and you see, I mean, if you never played cards before, now you see all of them. And you see that half are black, half are red. Here are your face cards, the Jack and the Queen and the King. You see the 4 suits, right? And you don't want to pick these ones, right? That's the game. So now, I have the AND game. AND was red, so AND was red and face. So red and face, you see the 6 cards that are red and face. That's how simple this is. There's nothing really to think about too much. You ask for, you circle exactly what is asked of you, and that is to be the face and the red at the same time. These are not red, they are face. These are red, but they're not face. So the only thing that it's and, right, is that red and face, so these 6. Now, or, you are happy with anything. Give me the black or the green marker. Okay, if I give you just black, you're happy, because you said or. If I give you just green, you're happy. If I give you both, you're happy. The only time you're not happy is if I don't give you any, right? So now, if I have or, red or face, you will be happy with any red card, even if it kills you, right? So any red card is okay. So we have 26 okay cards already. 26 okay cards from the red part, and they say any face. Well, we already counted these 6 faces, so I have additional 6 faces. So I have 26 cards plus another 6 for a total of 32 cards that will match the or. So counting is a little bit tricky. You have to be a little bit careful about that, not to double up. You can't just say, oh, 26 red cards and then plus 12 face cards. Well, you already, in these 26, you already counted these 6. So don't count them again, right? You count them only once. Now, we are going to have a mathematical formula that will be subtracting that. But right now, to understand why, you see the example, if I'm asking for a red card or a face card, when you count in these 26, you already have the faces included. You just add another 6 faces that are black, and you're done. So event A or B, we're going to have 26 red cards, and I'll put in parentheses which include 6 red face cards plus 6 black face cards for a total of 32 over 52 cards. You cut this in half, you get 16, 26. You cut this in by 2, 8 over what? 13. So probability is 8 over 13 to get this event. So probability of A and B was 3 over 26, and probability of A or B is 8 over 13. So there are 2 different probabilities, 2 different chances, and obviously the OR would have a better chance, better probability, right? Because more cards to play with. So we have one more definition, we're done. It's called mutually exclusive events are events that cannot happen at the same time, right? So heads and tails, it's either heads or tails. You can't flip a coin and get both. You can't pick black and red card at the same time. You can't pick face and non-face at the same time. You can't have raining and not raining at the same time. Right? So that's what mutually exclusive means. They cannot occur at the same time. So mutually exclusive events, two or more events. So two or more events are mutually exclusive if no two of them have outcomes in common. So two or more events are mutually exclusive events if no two of them have outcomes in common. And a quick example of this, flip a coin game. Event A, flip heads. Event B, flip tails. You can't have them at the same time. Another example of this, pick a card. Event A, red card. Event B, black card. So for these mutually exclusive events, the Venn diagram would be two completely disjoint events like this. So A and B, and they have nothing in common. So they're disjoint, so it's raining or not raining. You can't have raining and not raining at the same time. Now there are, if you want to extend this to more than two, because we only talked about heads or tails or red or black card, you can't buy a car, right, with a single color that it's black and red and white and gray and green at the same time. If you put stripes on it, sure. But the car needs to be a single color, and you can't have 5 different colors be a single color. So you're either getting a car that is black, or the car is gray, or the car is red, or the car is white, or the car is green. Right? So it's one of those things. They are mutually exclusive. Jokes never work when you translate, but one of the jokes we had when we were learning this in high school was, you see that red Porsche over there? I have the same black Honda Civic. It makes no sense, right? Okay, fine. It just means just end the lecture. Okay, fine. All right, let's go next one.